So, hello, my name is Antonin Novak. I am from Le Mans University in France, and today I'm going to talk about the bistable digital audio effect. Indeed, bistable system is a system that is a nonlinear system, and you can find it in physical world many systems. And at the university, we decided to create a student project, the goal of which was to create a bistable digital audio effect, to see how it sounds and to see what kind of audio effect it would make. So our two students, Alexander Ramirez and Vikas Tokala, have been working on this project, and myself and Frédéric Ablitzer and Manuel Melon only supervised this project. Alexander and Vikas unfortunately can't do this virtual presentation, so it's on me to present their work. So I will start with introduction, theory, and demonstrator that the students made, and then I will show you the discretization procedure and how the effect sounds. So let's start with the introduction and theory. Basically, if you want to understand what a bistable system is, you need to start with mass spring system, which is described by this equation where you have these coefficients: mass, damping, and stiffness. You have input force and output displacement. So basically, you are pressing this system and then you have output displacement. This system has its own resonance frequency or natural frequency, which is given by this equation. If you want to complicate the system a little bit and create a nonlinear system, you can add, for example, a cubic nonlinearity here, so alpha becomes, well, it's still linear stiffness, and then you have beta, which is nonlinear stiffness, and the stiffness becomes nonlinear system or nonlinear one, depending on displacement. This equation is a very well-known equation. It's a DAFX equation, which has already been used for audio effects. If you want to create a bistable system, there is just one small step to do, which is introducing this minus sign for the linear stiffness. And so now you have this equation, which is a bistable nonlinear system. So the stiffness is still nonlinear. The only difference between this one and the DAFX equation is this minus sign here. And this system is quite interesting because it can have two stable positions. This is why we call it bistable. If you plot the restoring force, so this force over displacement, so you can have this curve minus k1x plus k3x cubed, you can find two stable equilibria and one unstable. Basically, this is very often represented by this picture or by this system when you have a mass and then two springs. So imagine a mass and one spring going up, another spring going down. These springs are compressed. So now, if there is absolutely no force on the mass, then it stays in its unstable position, but usually doesn't. If there is just a tiny force on one side or the other, then the system will suddenly go to one of its stable positions. And so this system can have three kinds of oscillations. The first kind is called Interwell Oscillation, the other one is Interwell Oscillation, and the third one is the chaotic one. So the Interwell Oscillation is the one where the system oscillates around one of its stable positions, either for low or high amplitudes. The Interwell Oscillation is an oscillation where the system oscillates around both, well, it goes through these stable positions. And the chaotic one is when sometimes it stays in one position, sometimes in the other, and sometimes it goes through. And this is what we call chaotic oscillation. To really see how these oscillations are working, our students made or created a real-world system where here we have a loudspeaker that's attached, or basically it's the rest of a loudspeaker. You have no membrane, you have just a spider and stuff, but basically the motor is there, so it can be used as an input force. And then here you have a transparent membrane on which is attached a small piece, metallic piece as a mass. So the video recording is available at this address, so I'll go here. It's at the bottom of the page. And so I will start this video recording. You have the loudspeaker, or the rest of the loudspeaker, the membrane, bistable membrane, and right now it's on its first position, and the second one will be a little bit lower. So I will start the music or a sinusoidal low frequency wave, and now it starts to vibrate. It oscillates around its first stable position, and then I will increase the force just a little bit, and it will start to go to the second position and then back, so it will, you see, it's now oscillating between the first and second positions, so interwell oscillation. And now I decrease the force again, and it's stayed on the second stable position. And then we have suddenly a snap through to the first position, so kind of chaotic behavior. So thanks a lot to Alexander and Vikas for the work they did. So they did it very well, and this demonstrator really shows well how this system works and what these oscillations are. So let's go back to the presentation. So now we know how it works, what it is, and we would like to implement it as a digital effect. So our students used the simple differences schemes to make this analog equation digital one. So basically they just used displacement and velocity and acceleration and put these equations to the first one to get this final, almost final equation when you have input force, displacement, and then some coefficients A1, A2, A3 that are described here. Ts is the sampling period, and these A1, A2, and 3 depends only on mass, damping, and stiffness, linear one and nonlinear one is here. First, what we can see here, the force is only here, and this n-1, so the input is already delayed by one sample, so we can replace it by Fn, so just removing latency of one sample, no big deal. And the second step we did is, instead of having the output displacement, we used velocity for one simple reason, is that if you want to play your system through loudspeaker or just play on headphone, basically the loudspeakers inside the headphone or loudspeakers itself are monostable systems, and if you want the displacement of the output to be bistable, you can damage the loudspeaker. So a better way is to use velocity, which still describes this bistable system and sounds quite well. We have also tested the acceleration, but from our point of view the velocity was quite nice, and we'll see at the end. So that's it. We have the force, input force, the output velocity, and then our four parameters: mass, damping, K1 and K3 for stiffness, linear one and nonlinear one. We decided to tune the effect a little bit. First step we did was to put K equals to K1 and K3. So instead of having four parameters, which was quite difficult to tune and to play with, we decided to remove one of these parameters and to put these parameters together. So K is now a nonlinear parameter for the stiffness. Here, when you have the restoring force as a function of displacement, you can see how it behaves if you increase K. So K is equal to 1 for the blue one, K is equal to 5 for the red one, then yellow one is 10, and the purple one is 15. So with this coefficient K, you can increase and decrease the degree of nonlinearity. The second step we did, instead of having mass as a parameter, which is quite difficult to have and to tune, we decided to tune the F0, so resonant frequency, which is described by this equation. Even if this equation is for linear systems, we decided to use this one. So we have three parameters, the final parameters to tune: F0 resonant frequency, C damping, and K nonlinear parameter. So our students created a VST plugin coded in the Juice interface, and then we added an online demo application. So the VST plugin includes these three parameters: resonance frequency, damping, and nonlinearity, K, and then two parameters, extra parameters for input gain and output gain to play a little bit with the input and output. So again, at the same address, you can find the VST plugin. You can find either compiled version for macOS or Windows, or if you want to compile it on your own, you can do it. The Juice project is available here. So let's go back to our VST plugin. I will show you rather the online demo application, which is the web audio API. And so it's again the same address. It's available here, and we have these three parameters: frequency, damping, and nonlinear parameter, and then input gain and output gain. I will put bypass first and play how it sounds. So this is the piece of just return music playing, and then I will switch on bypass and play. And here you can see the restoring force, and then the output displacement, and these gray dots shows you where the displacement, so the maxima and minima of the displacement. And you can see that the system is playing around one of its stable positions. The second preset here is quite different. The sound is also different. These are interwell oscillations, where the system is oscillating through both stable positions. The third one is also interwell oscillation. It's just tuned a little bit differently. And then finally, preset 4 is for chaotic oscillations. You can see how it oscillates between first and second position, and it's quite weird to hear it. And then you can play with it. You can change and tune to decrease the output gain. So you can play with it as you wish with either this web audio API, which is available online, or you can download the VST plugin and play with it. Okay, so thank you very much for your attention. And if you have any question, or if you want to know about more, you can read the paper and you can contact us. The email address is available in the paper. Thank you. Bye.